I want to apologize to those of you that are watching the recording because it is the day before spring break and I have some people that will probably talk a lot. I'll try to make this as clear as possible.
Mr. Moore, I'm old.
Jessica, do you press
Yeah.
You won't have to worry about it.
That's Rithy's voice. You'll hear that, I'm sure, throughout the hour. Yesterday we had spent some time looking at the energy involved in dissolving an ionic compound. There are three different delta H's. The first delta H has to do with the solute breaking apart, and that requires energy. So delta H1 is going to be positive all the time. The second delta H is the energy involved with the solvent breaking apart, making room for the solute. That's going to be positive too, because you have to break the water molecules apart from each other. The third delta H is the attraction of the positive, well, not positive, negative, the attraction of the solute in the solvent. That delta H might be positive and it might be negative. So we have a equation that looks like this. SOLN for solution. That's equal to delta H1 plus delta H2 plus delta H3. This delta H3, this is the solute and solvent interaction. When would that be positive?
when it's endothermic?
Yes, when would it be endothermic?
Repelling.
Right. And what kind of solute and solvent would tend to repel each other?
Polar, non-polar?
Right. When your solute is polar and your solvent is nonpolar, or vice versa, they don't like each other and they're not going to tend to want to interact with each other. That's going to give you positive, positive, positive for your all three delta H's, and it's probably not going to dissolve. So a polar solute with a nonpolar solvent, or the other way around, is not going to dissolve spontaneously. This thing right here is the breaking apart of the solute. That's related to the lattice energy. Now, I put a negative sign in front of that because lattice energy is always a negative value. That's in the energy involved when ions join together to make an ionic compound. This is the opposite process. This is taking the ionic solid and breaking it apart. So we have the negative of the lattice energy. Now, that means that this term is going to be a positive delta H because, here's an example. The lattice energy of sodium iodide is negative 686. That's when sodium iodide ions come together, that gives off 686 kilojoules. Delta H1 then is going to be positive 686. It's the opposite of the lattice energy. Now the question is, what is the enthalpy of solution per mole of solid NaI? The delta H solution has 3 delta H terms here, but when I look up here, I only see 2 delta H's. Can I do the problem?
Yeah.
Yes. Why?
You only have one unknown.
What?
Don't you know the overall enthalpy?
You don't.
Oh.
Did you find
But what do you know, JD?
The enthalpy of hydration is the H2 and H3.
Yes, when you see the term enthalpy of hydration, that has to do with the water moving out of the way and bringing the solute in and then interacting with it. So these two together are the delta H of hydration. Delta H of hydration, enthalpy of hydration. So I wanted you to see this, this example because if you ever run into a problem where it's talking about the enthalpy of hydration, that covers 2 delta H values in one. So the answer to the question is, what would be the heat of solution? They're making ice cream next door too. Signa, would you mind closing the door?
Tell them to stop.
Tarun will do it.
Can we go get some ice cream?
Well, if they made any for us, they'll bring it over.
You're not gonna get any.
Really?
I call dibs.
I know someone from the art class. I'll just like.
Perks of having a good relationship with Miss Edan. I'll be there after this hour.
She hates me.
What kind of relationship?
Mr. Moore, you're on video.
Tell the world, Eric. Okay. So anyway, the delta H here for the 1 is positive 686. Oops. And then the heat of hydration is given at this. Now you don't change the sign on that thing. It's negative 694. That means this delta H term is always positive. So if those added together are the heat of hydration, that makes this thing a very negative number. So the water and the sodium ions and iodide ions are very compatible with each other because they have a big negative attraction, big negative heat of attraction. So positive 686, negative 694, that adds up to a heat of solution of negative 8, a whopping negative 8 kilojoules per mole.
Too fast, too furious.
Does that make dissolving NaI spontaneous or not spontaneous?
Spontaneous.
Okay, what does it take to make a spontaneous process?
Isothermic can increase in
It depends on the situation.
It does depend on the situation,
But on this
because you have these two terms. But we decided for ionic compounds, delta S dissolving the ionic compound is going to be a positive. An ionic compound will always get more disordered when it dissolves.
a low delta H would.
So we know for sure this is positive, temperature score is positive. And then the delta H term, if it's negative, that's definitely going to make a negative delta G. It always does, no matter what the temperature is. What if the delta H is positive?
It has to be a pretty low positive.
Right, or you have to have a high temperature.
Yeah.
Right, so low positive values for delta H still will mean that the stuff will dissolve. That's like ammonium chloride. When you dissolve ammonium chloride in water, it gets cold. It dissolves spontaneously, but it gets very cold. That's because the delta H is positive, but it's not too positive to make it not dissolve. Okay, so I wanted to review that. And then we're going to spend some time today looking at dot structures.
Dot structures.
Yes. Lewis dot structures. You took a few notes on that yesterday. Would you go to the next slide?
I remember the first reading was you asked us to draw a structure of some sort of like alcohol, and I was like, do you mean like a Lewis dot structure?
Funny.
I don't know.
First reading quiz.
Yeah, first reading quiz.
You pass it?
No, of course not.
So you wrote this down yesterday. I think we quit after this yesterday, didn't we?
Yeah.
Okay.
I don't think so. I think we have
No.
Go to the next slide.
honestly.
Oh, wait, time, don't. I should have had a step 6 here. I don't know why I didn't. I forgot.
Probably because you wanted to.
Would you write down a step 6? I can give it to you in 10 words or less.
Smiley face.
Is it just difference in electronegativity?
No.
Oh, I was close.
That was for you to do.
Oh.
So, number 5 says if you have a dot structure and you have too many electrons in there, you have to use some of them up to make double shift bonds. But what if you don't have enough electrons? Well, how do you add them in? That's what I have to address in number 6. If you need more electrons, that's 5 words. And now I'm going to count my words. Add to the central atom. This is not going to be comfortable for you at first because there are some times where the central atom's already going to have 8 electrons running. It's following the octet rule, but you need more electrons, so you're going to have to stick them on the central atom and give it more than 8. You've been conditioned, and appropriately, to assume that everybody needs to end with 8 electrons. But you're going to learn this year that they don't necessarily have to.
We don't have like 2 exceptions.
Okay.
The
Yes.
boron and the-
Boron is an exception. Boron is very small, so it winds up being stable with only 6 electrons around it instead of 8. But you can also have something like PCl5. PCl5 has a phosphorus in the middle attached to 5 chlorines. Well, the only way that can happen is if phosphorus has 10 valence electrons. And this is a stable molecule, it's perfectly fine. So yeah, you are going to run into cases where you're going to have more than 8 electrons in the central atom. Get used to it, it'll happen a lot. The most common is where you have 8 around everybody. But these exceptional ones, they show up. They're still exceptional, but you'll deal with it. Spencer, let's go to the next slide, but then move the shade up to only have one compound in there. That's good, thanks.
Selenium fluorine.
Yeah, we didn't do this yesterday, right? We didn't do any examples?
And the selenium dichloride, because
Yep.
Just fluoride. It's not molecular as I It is molecular.
It's not.
Is it molecular?
Essie's on that side.
Oh, it is.
It is.
Congratulations. Oh, no, you're not. You're saying something. That's sarcastic.
You need to do these the same way every time. I know that I've just given you now 6 steps, and you think, oh no, I don't have time for that, I need to keep going faster. Do all 6 steps every time. Get into a routine. You can. Don't complain either. You can do it very fast, but don't skip anything. The first step is to count the number of valence electrons. Don't skip that step. So we have, selenium has how many valence electrons?
6.
6. Where's 2 from?
It's
Oh,
right there.
you looked at strontium, didn't you? Yeah, selenium has 6. And then 2 fluorines, each of those have 7.
Right side below us.
Yeah. All right, so the fluorines each contribute 7 electrons, there's 2 of them. So we have 6 plus 14 is 20 electrons. We're going to have to come up with a structure that has 20 electrons. If we can't come up with 20 electrons, then we're not doing it right. So the next step is to put the least electronegative element in the middle. Which one is that?
So, SE.
The Fe, yeah. Fluorine is the most electronegative of all. So that's never going to go in the middle. Put the Fe in the middle and attach the fluorine atoms with single bonds at first. You may have to change the double bonds later, but only if you have to. After you've added single bonds in here, and you've gotten all your atoms accounted for, then you want to add lone pairs of electrons all the way around to everybody to get everybody 8 electrons. Now,
Just a question. How do you determine the valence electrons of selenium?
valence electrons are the outermost S and P electrons,
Yeah.
not including Ds. Ds don't count. So selenium is over here in the oxygen family.
Yeah.
In the last energy level, there are 2 S electrons in 4S, and then 4 electrons in 4P.
Okay.
So there's 2 and 4, that's where I got the 6.
Oh.
Shorter way to do that though, the Roman numeral at the top of the family tells how many valence electrons it has.
Oh, it does?
So above oxygen is that Roman numeral 6A, so it's got 6. Okay? After you've added all your lone pairs in here, now count the total number of electrons that we have. 2, 4, 6, 8, that obviously 2 electrons. So it's 8, 10, 12, 14, 16, 18, 20. That's got 20. We're looking for a structure that has 20. Everybody has 8 electrons around them. That's good.
Yeah.
For SEF2. That's all you have to
So
do.
you don't want this.
No, you're fine.
Anybody have any questions about that? It's pretty easy. All right, let's move on. The next one is carbon dioxide. You might remember carbon dioxide from before. CO2, step 1, count the number of electrons. We have how many carbon? 4. Carbon has 4. Oxygen has how many?
2. 6. JK, 6.
Right, and there's 2 of them. So 4 plus 12 is 16 electrons. We're going to have to make a structure that has 16 electrons accounted for. Put the less electronegative one in the middle. Which one is that? In general, the one that's written first in the compound is going to be the one that you put in the middle. In general.
Carbon's always good in the middle, though.
There will be some exceptions to that, but you can usually use that. If you're not sure, put the one that's written first as the middle end.
I mean, like, alcoholism.
Okay, now add electrons. Sorry. Add electrons to this thing so that everybody has 8 electrons around them. Like that. Now evaluate how many electrons you have. 2, 4, 6,
20.
8, 10, 12, 14, 16, 18, 20. It's got just